right, ladies and gentlemen, this is the video lecture for today. I am in the building, so you might see me, but I am interviewing prospective assistant principal candidates today, which is why you're not seeing me in class. I'd like you to please get out your notes on acids and bases that we've been going over, your reference table, your calculator, and the sample problems from lecture. So we're going to be in this section talking about the rest of the initial pH calculations, meaning the sort of basic fundamental level pH calculations that we need to be able to do in AP Chemistry. So just as a reminder to both classes, period 5, we did this problem. Period 6, we have not yet done this problem. We had to skip a few because of the snow or early release day last week. But you should remember, everyone should remember from the work that we've been doing, and find this in your reference table as well, that we have this relationship that H plus times OH minus equal to 1 times 10 to the negative 14. Period 6, you hopefully read that in the textbook. Period 5, we talked about that last week in class. We also know the mathematical definition of pH, that pH is the negative log of the hydrogen ion concentration. Again, this is really the two big things that we're starting with at this point that we've discussed. We're going to talk about the rest of the pH calculations because there's more than simply these relationships. Now, this question right here, which is sample question number 11, what is the hydrogen ion concentration when the pH is 3.76? Period 5, again, we already talked about this problem, but period 6, we have not yet discussed this. Based on this relationship right here, pH is equal to the negative log of the hydrogen ion concentration. If you are going in the opposite direction, meaning I give you the pH and I ask for the hydrogen ion concentration, exactly right here. You can't simply divide both sides by a negative log. That's not the way that math works. You have to take each side and make it the exponent for 10. And because there's a negative right there, we have that hydrogen ion concentration in this relationship is also equal to 10 to the negative pH. Now these first two are on your reference table. H plus times OH minus is equal to the autoionization product constant for water, which is 1 times 10 to the negative 14. And pH is equal to the negative log of H plus. This third one, however, that H plus is equal to 10 to the negative pH, that isn't, because frankly they've already given it to you. You just need to know how log rules work. So again, picking up with this particular problem, what is the hydrogen ion concentration when the pH is 3.76, and you need 10 to the negative 3.76. But you can't leave it at that. Do not leave that as your answer. Actually calculate it out. I don't want to see any decimals in exponents when we do that math. So if you punch that into your calculator, 10 raised to the negative 3.76 power, you get an answer of 1.74 times 10 to the negative 4th molar. And that is the final answer. Okay, so showing the same sort of stuff right there. Which brings up this next point, pAnything. What does lowercase p mean? It's not a random number, it is actually describing a mathematical function. If you have a small p out in front of something, it means that you need to take the negative log of that thing. pH means take the negative log of the H, meaning the hydrogen ion concentration. That's where that comes from. This is important for us because of this relationship right here. pOH equals negative log of the hydroxide ion concentration. P is not something that is unique to the H plus concentration. We're going to use it a lot in this context as well, that pOH is equal to the negative log of the hydroxide ion concentration. And if you look in your reference tables, you'll see this is right next to the mathematical definition of pH. They're both right there. Like P of something means you take the negative log of that thing. Well, you can also, we're not simply limited to hydrogen ion concentration, hydroxide ion concentration. We also talked about this autoionization product constant for water, this 1 times 10 to the negative 14, this Kw value. If you take pKw, then you are simply taking the negative log of that Kw, that constant value, that 1 times 10 to the negative 14th. And if you do the negative log of 1 times 10 to the negative 14th, you get 14.0. And that's where the pH scale comes from. It wasn't just a random, oh, I guess we'll go up to 14. It's saying, all right, the autoionization product constant for water is 1 times 10 to the negative 14th. If I take the negative log of that, I get 14. Additionally, we have these relationships right here. Because H plus times OH minus is 1 times 10 to the negative 14th, if you, aka Kw, right, that's a relationship that's in your reference table, right, H plus times OH minus equals 1 times 10 to the negative 14th. If you take the negative log of everything that's involved in that formula, you get pH plus pOH is equal to 14. And find that on your reference table. It's going to be in the equilibrium section with our fundamental acid-base calculations right next to all the other ones. This formula, pH plus pOH equals 14. When you combine it with the other ones that are on the reference table, that pH is equal to the negative log, the hydrogen ion concentration, that pOH is the negative log of the hydroxide ion concentration, and then the H plus times OH minus is 1 times 10 to the minus 14. These 4 equations are all fundamental to us in doing acid-base chemistry because they're all cyclical. They all loop back to one another. And you should hopefully be able to see that if I simply supply you with one of the values, either pH, pOH, hydrogen ion concentration, or hydroxide ion concentration, these 4 relationships will let you calculate the other 3. I only need to give you one for you to be able to get the other 3. And quite frequently, in the problems that we're going to be doing coming up, that's exactly what's going to happen. I'm going to give you one, but you're going to need something else, so you need to do a little bit of math to get the additional one. Now, that's well and good if I'm specifically giving you H plus concentration or OH minus concentration, but it's much more common for me to give you the concentration of a strong acid like HCl. Say the concentration of the HCl is 0.01. Well, that's not explicitly H plus. Yes, it's related, but it's not explicitly. So let's talk about if we actually pull in a strong acid. In solutions, your strong acid is going to be your only source, typically the only source of the hydrogen ion. Yes, water auto-ionizes, but it auto-ionizes only a very, very, very small amount, to the point where if you were to add the amount of H plus that the water contributes to the amount of H plus that a strong acid would contribute, and take the pH both with and without the contribution from the water, it's going to be the same either way, at least to the level of specificity that we're looking. Any difference in pH is not going to be detected until, like, you're at the 4th or 5th decimal place out. So it's enough for us to say that our strong acid is going to be the only source of hydrogen ion if we're in solution. And therefore, knowing what we know about strong acids, we can calculate the pH directly from the strong acid concentration. Remember those brackets around the SI mean that the strong acid concentration. Brackets stand for molarity. For example, sample problem number 12 in the packet. What is the pH of a 0.04 molar solution of perchloric acid? Here's what I mean where I haven't told you the hydrogen ion concentration. I've simply said the concentration of the acid. Well, no big deal, we can handle this problem because of this relationship right here. If we write the acid dissociation reaction, we're saying what's going on when this perchloric acid is put in water? Well, it dissociates into H plus ions and perchlorate ions, H plus and ClO4 minus. But it dissociates completely, 100%, meaning all of the HClO4 turns into H plus and ClO4 minus. Which is going to mean for us, based on what we know about dissociation, that if the HClO4 concentration is 0.04 molar, and 100% of it dissociates, and we look at the molar relationship between the products and the reactants, then we're also going to create 0.04 molar H plus and 0.04 molar ClO4 minus. And we can do pH calculations with that. Because the strong acids completely dissociate, your concentration of your HClO4 is going to equal the concentration of the H+, which is going to equal the concentration of the perchlorate ion, which will be 0.04 molar. And we can do our pH calculations with that because we just said H+, 0.04 molar. So suddenly we do have our value that we can do our math with. So doing that math, we're going to take the negative log of the hydrogen ion concentration because that's how we calculate pH. Simply plug that in, and I get a value, I get a pH value of 1.40. Again, a reminder that you want to make sure you're taking your pHs to a minimum of 2 decimal points because we're going to be seeing some subtle changes that if we're not going to the hundredths, we might miss later on. So we're just getting into a good habit of taking pHs to 2 decimal points now. Follow-up question. An aqueous solution of nitric acid has a pH of 2.66. What is the concentration of the nitric acid? We're working a little bit backwards here, but it doesn't really matter because it's the same idea. I'm going to start with this pH value of 2.66 because I know that 10 to the negative pH is going to be equal to my hydrogen ion concentration. And because this is a strong acid, nitric acid, it completely dissociates. It turns into nitrate and hydrogen ion. So whatever this concentration is for the hydrogen ion, it's going to be the same thing as the concentration for the nitric acid due to that complete dissociation. So I do 10 to the negative 2.66. I do not leave that as an answer. I actually plug that into my calculator and 10 power negative 2.66, enter, get a value. I get a value of 2.19 times 10 to the minus third molar. That's my hydrogen ion concentration because that comes from my pH. But right here, H plus is going to equal the nitric acid concentration as well. So it is also my HNO3 concentration, which is the answer to the question. So if I give you the concentration of a strong acid, I am giving you information that you can use to get pH. Now, going in the opposite direction, strong bases, same thing. They undergo complete dissociation. 100% of them ionizes, which means that if I give you the concentration of a strong base, you can calculate the pOH from the concentration of the strong base. And because you can calculate pOH from the concentration of the strong base, you can also calculate pH from the concentration of the strong base because they are all related to one another. So, sample question number 14. What is the pH of a 0.011 molar solution of calcium hydroxide? I will say this right now, right here. I am going to try to get you on those group 2 hydroxides every opportunity that I can take. I am going to lay traps for you because the difference between this question and the previous questions is how does this dissociate? There's a slight difference here. While having a 0.011 molar solution of calcium hydroxide will lead to having a 0.011 molar solution of the calcium ion, I repeat, I do not have a 0.011 molar solution of the hydroxide ion. And the reason is this is a group 2 hydroxide. So because of this 2, because I'm generating 2 OHs there, 0.011 molar initial concentration here, yes, it gives me 0.011 molar here because of a 1-to-1 ratio, but I'm going to have a 0.022 molar solution of hydroxides because I got sort of double my money's worth. Saying this again, I will try to trick you with this. I will be giving you the group 2 hydroxides, and I might just give you their name, not their formula, to see if you remember that they are going to have 2 hydroxides for every 1 mole of the ion, of the ionic compound. This is the difference between the strong acids and the strong bases. You have to bear that in mind, that I'm going to get more, in this case, calcium hydroxide, strontium hydroxide, barium hydroxide, right? It's like a 2 for 1. So having done this math up to this point now, the rest of the problem is going to be very similar to the last one, meaning I've gotten my hydroxide ion concentration. I'm looking for pH. There are two ways that you can get pH once you have the OH minus concentration of 0.022 molar. And we're going to talk about both of them. This, to me, is the first thing that I tend to think of doing if I'm looking for pH. I tend to go the route of calculating the pOH and then subtracting from 14 to get the pH. So this is sort of my personal preference when it comes to doing this type of problem. I know that I have the hydroxide ion concentration. I know that I'm looking for pH. One of the ways that I can do that is get the pOH and then subtracting from 14. So I'm going to take the negative log of the OH minus concentration, take the negative log of the 0.022 molar, and get a pOH value of 1.66. That's not my answer because that's pOH, but I'm pretty darn close to my answer because all I need to do now is subtract, because pH plus pOH is equal to 14, and I can get a pH value now of 12.34. But that's not the only way to do it. Both ways require the same work at the beginning, meaning you have to get up to that point of realizing that you have a 0.022 molar solution of hydroxide ions, but you could also use this, right? Once you get that hydroxide ion concentration, you could also go to the autoionization product constant for water, and this relationship that the H plus times the OH minus is going to be equal to 1 times 10 to the minus 14. After all, we're looking for pH, so isn't a way to find pH is through the hydrogen ion concentration? Yes, absolutely. So you can plug in for your OH minus concentration, the 0.022 molar, right, divide 1 times 10 to the negative 14th by 0.022 molar, and you get a hydrogen ion concentration of 4.6 times 10 to the minus 13th. I got 4.55, taking it out to an additional sig fig. And then we're looking for pH, so really that's pretty gravy at this point. We're just going to do the negative log of the hydrogen ion concentration, because that's the mathematical definition of pH, and we get a pH of 12.34. Oh, look at that, it's the same thing, multiple ways to solve the same problem. Gosh, that doesn't sound familiar at all in chemistry. So it's about which way you see it. I will tend to present these problems in terms of pOH and subtracting from 14 to get pH, etc., because that's how I tend to see them. This manner using H plus times OH minus equals 1 times 10 to the negative 14th is absolutely 100% completely correct as well. Because this whole relationship between pH and pOH and hydrogen ion concentration and hydroxide ion concentration is very, very cyclical. Multiple ways to calculate the same thing from the data that's given. I'm going to skip this question and talk about percent ionization. Percent ionization is simply a way to measure the acid strength for weak acids. Typically, percent ionization is not something that you talk about with respect to strong acids because they have very, very high percent ionizations. Their percent ionizations are 100%. Like, that's what it is. The 100%, maybe they're like, 99%. We're assuming that they're 100% realistically. So percent ionizations for us is a way of comparing relative strengths of weak acids, because we're saying, look, how much is this weak acid capable of ionizing? How much hydrogen ion is it capable of generating? And we can calculate that based on an acid dissociation reaction for weak acids. Notice this is a weak acid dissociation reaction because it has a double arrow indicating that the reaction goes forward and reverse, meaning once it's dissociated, it is also possible for the H plus and the A minus to reassociate and to make HA. And the formula that we have for this, which is not on your reference table because you don't need it because it's a percent formula, is shown right here. The percent ionization is equal to your hydrogen ion concentration over your HA, your weak acid concentration, times 100. And this is a very, very typical part over whole percent. That's how you find percent. And what we're measuring here is we're saying that HA that we start with, that's our whole. That's your starting point. How much weak acid do you have? That's the whole thing. And then the question is, how much H plus does it generate? Meaning, how much pops off? What is the part? Percent ionization is just like any other percent. It's part divided by whole. So you just take the H plus concentration, you divide it by your acid concentration, your HA, you get your weak acid because not all of that HA dissociated, and you can get percent ionization. So we're going to do a practice problem with this. What percent of the acid is ionized in a 0.1 molar formic acid solution with a pH of 2.38? Percent ionization, part over whole. H plus, that's our part. HA, that's our whole, times 100. Do we need to know what formic acid is? Not in the slightest. Do we need to know that it is a weak acid? Yes, we do. Well, we do know it's weak acid because we know it's not one of our strong acids. So we know that it is incompletely dissociating. So in order to find its percent ionization, we need the H plus concentration and we need the HA concentration. And we have two numbers given to us in the problem. 0.01 molar formic acid solution, pH of 2.38. 0.01 molar is your HA concentration, because that's the weak acid. The weak acid on its own, before you put it in water, or when you're figuring out how much you need, that's your whole. This thing right here, that's your whole. That's going to go on the bottom. The problem also gave us pH of 2.38. We need this H plus ion concentration. Problem didn't give us that directly, but hopefully by now you're starting to see that if the problem gives you pH, it really gave you the H plus concentration. That's what you really have. Because times with a negative pH is equal to your hydrogen ion concentration. And that's exactly how we're going to get that top number. That whole, that part, excuse me, how much of that 0.1 molar initial acid concentration dissociated off from pH plus ions. So we're just going to do times the negative 2.38. Do that out. Don't leave it as that. That's not pH plus concentration on its own. Actually, do the math. And I get 4.17 times 10 to the negative third molar. This is our H plus concentration. That is our part. For part of the whole. Now the math is super easy because all we're going to do is divide the part in 4.17 times 10 to the negative third by the whole, or 0.1 molar. This is saying that you started with 0.1 molar, but only 4.17 times 10 to the negative third associated. So what's the percent ionization? Do part over whole, and it turns into 4.17%. And that's the percent dissociation of formic acid. Like I said, these percent dissociations are typically about 5% or less. So, and we see with a 4.17% dissociation, it's very, very typical for a weak acid.